So, all right, I will begin with a word of prayer. Dear Father, we thank you for this day, and I thank you for your creation that we can study and enjoy. Help us to understand it a little bit better today, Lord. In the name of our Lord Jesus. Amen. Okay, so this is the example we looked at last time, solving the Laplace equation, between two conducting planes, and we're given the voltage applied here is a particular function of y, right? That was the deal. We talked about how you can ignore z because you have no z dependence, so it's just a problem in x and y, and you just put the z back in at the end of the problem. And the way to solve this is by separation of variables. So we suppose that we've got a product of x and a product of y, and solve Laplace's equation. When you do the differentiation and you plug it in, you learn that you should just have, both of these being equal to some constant, which we decided to call Moore's law. And so we're sorting back through the boundary conditions. We have both y of a and y of 0, 0, and the boundary condition 3 and 4. Well, they're a little more interesting. Boundary condition 3 is perhaps the most interesting. Boundary condition 4 is, super helpful in that it eliminates a good bit of the analysis. All right, so continuing on, there are three cases to consider. Either upsilon 0, we get nothing. Upsilon is negative, we get nothing for y. But the positive constant is where we get exciting, interesting solutions from. Namely, we learned that the beta, which is squares to give upsilon, it has to be n pi over a. So we get our sort of characteristic solutions, sine of n pi y over a like this. All right. And then once you know that, well, you know the value for upsilon, so you go back to your x differential equation, and you got this thing to solve, which you remember last time I did Cauchys and Cinches, and then I was like, oh, that hurt. I realized, this is the one you got to do exponentials for, because exponentials are your friends in this context, because it's easy to implement the voltage, the potential goes to 0, and as x goes to infinity, it forces us to have none of this, but just that. So lo and behold, we find that our typical characteristic solution for x has the form e to the minus n pi x over a like that. Now, we still haven't implemented boundary condition 3. To do such, we put everything we have together into one big swooping solution, and basically it's sort of undetermined coefficients on steroids. If you've had differential equations, the a sub n's are undetermined coefficients, which we have to determine with the boundary condition 3. So boundary condition 3 says v of 0y has to be this, but it also has to be that. And then our goal is to find formulas for a sub n, right? That's what we're trying to do. And we did that last class, kind of, sort of, by quote-unquote Fourier's trick. Now, the critical mistake in last class was right here, because I didn't do the algebra. If we do the algebra with imaginary exponentials, as is the refined and polite way of doing trigonometry, you get 1 over 2i, you do the I theta, you do minus I theta for your sine, and here's your sine beta. Do algebra, regroup stuff, and you know what? The product of sines is not a sine, it's a cosine. Duh. So I had sine here last time because I'm an idiot. And that cost us about 10 minutes of class, I think. But anyway, or maybe 20 since I'm not reviewing. But so anyway, it's a cosine of the difference in sum like so. So when we integrate this product of sines, we end up with the integral of the difference of these cosines. But those are straight up going to give you integer multiples of sine, of pi, inputted into the sine, and those are just straight zeros. There's nothing, we were thinking last time to make that stuff go away, but there's no thinking there. It's just manifestly 0, because sines are orthogonal in this sense. They're independent. On the other hand, if we integrate sine with respect to itself, we get a over 2. So the long and short of it is we have this proposition. The integral of sine of n pi y over a times the sine of k pi y over a, integrated from 0 to a, dy. Well, we can see that that's a over 2 times the Kronecker delta of nk. So basically what this does is if you've got an infinite sum, right? If you've got an infinite sum, if you can hit it with one of these things, it'll zero out the sum and just eliminate everything but one term. This is Fourier's trick. And so when we apply that to the infinite series that's forming the so-called sine series that's forming our potential, well then this happens, and then we pull the integral inside, but that's a Kronecker delta, which is the natural enemy of the infinite sum, and such it leaves us with a over 2, a sub k2, then solving for a sub k gives me this. Lo and behold, we found our formula for the kth coefficient, and of course I changed that to n next, because who wants to have a formula in k? All right. And there you go, that was the general solution to the problem that's example 1. Now, of course, once you have that, you can solve a variety of related problems. So that's what I did next. I was like, well, okay, if you happen to have a boundary condition, a voltage at the end of the slab, which was given to have this form, then we could go back and we can just like read off from this that a sub 3 is 10, and a sub 7 is like minus 40, and it's 0 otherwise. And then we go back to like my solution, and we just write down, these are the only terms that survive. So we don't actually have to do the Fourier integrals if the boundary condition is stated as a Fourier polynomial. Did you get that? If the boundary condition has the same structure as the natural solution set for the Laplace problem, then we don't actually have to integrate, we can just match up stuff. These make nice cheesy test questions, obviously, right? So, on the other hand, you could be like Griffiths and say, well, what if the potential's constant? And then, fine, I'll follow you and down this merry path. If the potential's constant, then we have to do this integral, which gives us this, which gives us this. Now we're back into that kind of stuff we were doing last time needlessly. And namely that it's either 0 if it's even, or if it's odd. You can see from here that I switched the story around in my mind somehow earlier today, but I fixed it in black, so there it is. So 0 if it's even, because that cancels. If it's odd, it gives you 2. And so we're left with these being the non-trivial coefficients. Put it all together, there is your grand, glorious solution in the case that we have the voltage held constant at that end part. All right, so like we have that the end cap is a constant voltage, and then you got 0 volts on the top, 0 volts on the bottom. The idea is there's some kind of like very small insulator between where we have the voltage held constant at the end and the infinite conducting metal equipotentials that are ground. All right, so like that's we're ignoring whatever details there are in terms of that edge, and that's also where the mathematics breaks down if you're fussy. Because we don't have continuity at the corners, I don't think. And if you like, you can look at Griffith's figure 318 for a picture of that thing, kind of. And he actually has a stone cold formula for this one, like inverse tangent or something or other, but who cares? I mean, I care a little bit, but I don't have enough time to care that much. So the next problem is this one. So this one's a little bit different in that this time we have voltage 0 on the top, on the bottom, and voltage fixed on this side and that side. So these are the boundary conditions. They're a little bit different than the previous set, all right? But the solution technique remains the same. See, there's no, it's featureless in terms of Z. There's a Z symmetry here. There's a translational invariance in the Z sense. If there's translational invariance in Z, that means that you don't have to have there's no non-constant Z dependence in your solution. So we can suppress the Z, all right? And like I wrote in the red there. And then separate variables just like we did last class, like so. Getting to the point, we're still up against the same boundary conditions for Y, so the story of upsilon is going to work out the same. We're still going to end up with just the case that upsilon is n squared pi squared over a squared, gives us non-trivial solutions for Y, namely these signs, and as such, that forces this upon us in the X. But this time, I will be redeemed. The Cauchys and cinches are helpful, because this time you want these, but you don't want those. The reason being that the boundary conditions are like even, the way they were set up. So this is like, generically speaking, you'd have this, I started calling it the potential. I have no apologies for this. This is the right thing to call it. It is the potential, because it's not done yet. You're trying to figure out what the values of the A sub n's and the B sub n's. Once you figure those out, it's no longer a potential, it's just a potential. Right? It's like undetermined coefficients. They're undetermined until they're not, right? But if you don't determine the undetermined coefficients, then I have to take points off. This always happens. There's always some student who like sets out the solution and like, I figured it out. And I'm like, but it's all not set up. And then I take the points away. I warned them this was going to happen today, but I know that that's not going to stop them from doing it because it's like happened many semesters already. Well, you know, we mathematicians, we generalize a bit. I assume that there's a certain invariance of student features over semesters. But anyway, so that's like the general setup. But then the thing is, because we have this situation where v of b and v of minus b is the same, that suggests that we must just maintain, we're only going to keep the even part of the solution. So I throw out the sinh in x because that's odd. And so I can make do with Koch. Now, okay, this paragraph should properly be replaced with some sort of gory Fourier integration where you show all of the other coefficients are necessarily zero because of the evenness of the boundary conditions. I just spared you that, right? With this Boudard style argument right here. So he asked me if I was making fun of him, and I said no more than usual. But in my defense, when I first met Dr. Boudard, I said to him something like, man, I really got stuck in class today. I just don't know what I did wrong. It's so annoying. And his response was just coldly, yeah, I remember once when I made a mistake. Just like that. Just like, monster. It's just so, it's true. It's gracious. Anyway, I like Dr. Boudard. But he hurts my head sometimes, but it's good. Anyway, so we're trying to calculate the a sub n again, and so to do that, you multiply both sides by the sign, and then integrate both sides at the same time, pull the integral inside the sum, that's a Kronecker delta, it kills everything but that term, but this time there's a Koch riding along, so it's not exactly the same, but it's similar. Then you solve for the coefficient that you'll want, like that, and lo and behold, yay, general solution to the other problem looks like this. All right? And putting it all together, putting the z back in, there's your handy dandy solution. You just, you know, that's what you need in order to achieve that solution to the boundary value problem we were just given. And that's how it goes. And a final example for today, three-dimensional. This time, well, they've all been three-dimensional, but this one is genuinely three-dimensional in the sense that the translational invariance in the, in one of the, I mean, there's an end in the x, the y, there's no, it has to depend on all three, right? Because this doesn't go on and on, there's no x invariance, like we can't suppress the x and just have it about y and z. They're all at play. And in this case, same separation of variables goes through, like this, all right? But the difference is a little bit different. So like, the way to think about it is that the x is kind of special, so we'll treat y and z separately. And y and z are playing the same role that I did in the previous two examples, so we already know what's going to happen there. By the same boundary condition logic, we're going to get to like y prime prime plus k squared y and z prime prime plus l squared z equal to 0, because this and that are given, and that's 0. I forgot to write it, sorry. And so, and this is what Griffiths is smart enough to put k equals to m pi over a and l equals to m pi over b, not like me, just keep writing this and that again and again and again, right? So he's smarter, for sure. And great, so once you know that, that gives us this, but then x prime prime over x is equal to this. So you got to deal with that, which looks like this. So you solve, and lo and behold, you've got your characteristic solutions like this, that, and that. But d is 0, f is 0, and a is 0 because of the respective boundary conditions in x, y, and z, and that just leaves us this for our potential. And to get past the potential phase, we'd have to do the Fourier trick again, but instead of eliminating one sign, we have two signs, which means we're going to have to multiply by sign not once, but twice, and integrate not just with respect to y, but also with respect to z, in order to like isolate these coefficients and find the potential. So that looks like this. That's the formula for the nn coefficient. You just have to integrate like this. Griffith says z and y flipped here. I'm pretty sure he's wrong, because b goes with the z, not with the y. So the z's got to go here, and y is that one. So, yeah. Okay, so there's that. I was going to say, guys, I have a little something. Which is, these are solutions from like chapter 10 in Nagel's and Snyder. And I think they're currently pulled down from my website. I used to post it, but I think I pulled them down because I've been using them lately for class. So I don't want them to, just have these. So don't tell them. You guys aren't in there, right? No.
We're not.
So one of the things I should talk about here is, and I'll post this in course content for you guys, but this is the Laplacian polar coordinates. It turns out this is what it looks like in polar coordinates. Now these are math polars, so my apologies. I'm violating the sacred, division between math and physics notation. I have waxed physical in my notational choices here. Excuse me, mathematical in my notational choices. This should properly be partial squared u partial s squared plus 1 over s partial u partial s 1 over s squared partial u squared partial phi squared in Griffiths. But the techniques remain the same, right? And so, like, what does it look like to solve Laplace's equation in polar coordinates? Well, first of all, by the way, this is another example of Laplace's equation in Cartesian coordinates, but this one actually is subject to fixed derivative boundary conditions. That would mean what for us? Yeah, this is the other kind of boundary conditions. What does it mean if the normal derivative, I think these are normal derivatives.
It's a field.
It's a field. I think this means like no charge or something, because the field is, I don't know. But you could, that might be interesting to think about what that means physically. That's not going to be in here, obviously, but the math is here. Yay. Glorious detail. And then here's another one. This one's kind of similar to the ones we worked. I don't really care about this, though. I just want to show you guys the polar thing while I hand it out. So here's a solution of the Dirichlet problem on the disk using like math polars, if you'll forgive me. And so the basic technique is the same, guys. Like, this is the form of the differential equation, so we assume a product solution and then plug it in. And when you plug it in, it ends up giving you one differential equation for the radial part and a different one for the angular part. But since this is a function of r, this is a function of theta, it must be that in totality they're constant. But then the thing is with this, that's a Cauchy-Euler problem. That's an equidimensional differential equation. We know how to solve those. And this, of course, is a constant coefficient for the theta piece. But here, there's a little bit more because this is on a disk, right? So there's continuity. You need that pi and minus pi. Those are the same point, right? That's the negative x-axis. That's where that meets up, right? So if we're trying to solve this relative to minus pi, we do need that in our solutions. And anyway, so I reason through the boundary conditions here, and after the dust settles, I find my way to supposing that we need this kind of thing for the angular part of the solution, which then forces me to look at characteristic value n squared for the radial part of the solution, which ends up giving me this characteristic equation, which when you solve gives you the actual radial solutions, namely these things here, Cn r to the n plus dn over r to the n, all right? But the thing is, we're solving it on the disk, so the radius goes to 0. So because we want a bounded potential, we can throw these out because those blow up at the origin, which means we're just left with those, all right? And I also threw out the natural log solution that appears in there. And anyway, lo and behold, this is the potential for the Dirichlet problem on the disk. Some constant plus r to the n times all that. In order to find these constants, you have to be given more boundary conditions, and then you fit them using the Fourier trick again. You just basically take this and multiply it by sine or cosine to take off these coefficients as appropriate by the correct integration. But yeah, I don't think this is in Griffiths. Griffiths doesn't have, as far as I saw, a cylindrical example. This is essentially a cylindrical example, if you can trade the r's to s's. But anyway, my apologies, there's not much physics in here, right? Because I stole this from, Nagel, Sapp, and Steiner, but anyway, I'll shut up. So, let us talk about how to solve Laplace's equation in the other coordinate systems. All right? So the critical thing to know about is what is the form of the Laplacian in other coordinates, right? So, I'm not going to derive that in here because, well, that's calculus 3's problem, right? We just write them down and use them. If you'd like, I could test you on the derivation of the Laplacian and sphericals, but you guys probably like, it's okay. We can just assume that. What do you think?
Yes.
Yes, all right.
I think we're good.
We're good. Part of me really wants to go to the appendix and work all that out. All right, so here's the deal. We have this thing. So what we're looking at right here, this is the Laplacian, and so this equal to 0 is Laplace's equation in cylindrical coordinates, right? Now, we can work out what does separation of variables look like for this problem, right? Like, how would you do separation of variables on this problem? What would that look like? We start out by just saying, my voltage potential is something like, S of S, I guess big phi of phi, and big Z is Z, right? And in this, wild notation, if we do partial V, partial S, we've got S prime, phi Z. If we do partial V, partial phi, we've got S, phi prime, big Z. And if we do V, partial Z, we've got S, phi, Z prime, right? Where, of course, those primes indicate derivatives just with respect to variables of those products. And so if you plug that in to the differential equation, what happens for us? Plug that in up here. We've got, 1 over S, partial S of S S prime phi z plus 1 over s squared. I guess when we take the second derivative, we just get s phi prime prime, right? Big Z. And then finally we get our s phi, when we take a double derivative of z, that gives us big Z prime prime equals 0. Now, can I just, I don't want to write that all again. I just kind of point out to you that we can pull the phi and the z outside the s derivative, right? These two things are just functions of phi and z respectively. So there's no s derivative here. We can do this without any heartburn. And then what you do, divide this monstrosity by the whole solution. All right? And what that gives you is 1 over little s times big S, partial s, little s times big S. My bad. S prime, I should rewrite as, oh fine, partial big S, partial little s, plus 1 over, let's see here. In that one, the s and the z cancel. I'm just left with like a s squared, big phi, partial squared phi, partial little phi squared. And then finally 1 over z, partial squared z, partial z squared. Now, my bad. I've written these as partial derivatives, but it's not best because s, phi, and z are all just functions, respectively, of s, phi, and z. So those are not partial derivatives. They're actually total derivatives. Right. I can rewrite this as 1 over little s big S, eds of s, ds, plus 1 over s. Wait a minute, that's wrong. Big phi, d squared phi, dt squared plus 1 over big Z, d squared Z, big Z, dz squared equals to 0. All right. Good product. Well, anyway, I think there's something, all right, well, here's the thing. Is this right here is function of s and phi, right? But this over here is function of z alone, right? But I think Sam is right. I think we could do a product rule and like clean this up more. Now, I haven't worked that out yet. I was just trying to work it out with you guys at the moment. And so I think I'm going to stop here for the moment with that. But we could, at this point, we can already see that we can cipher that this and that must be constant. Because this is a function of z, and this is just a function of s and phi, which means that these both must be equal to a constant. If this whole thing is equal to big C, that has to be equal to minus C. Or upsilon, if you want to go back to that. Right? But, so that's just a start on how we would do cylindrical coordinates, all right? But the story for spherical coordinates is far more interesting. And it ties into the story for the rest of chapter 3. In particular, let's get into that. So, to start with, I need to write down, so to be continued, all right, to be continued. But here's the spherical case. We have the Laplacian of the potential is 1 over r squared, partial r, of r squared, partial v, partial r, plus 1 over r squared sine theta, partial theta of sine theta, partial v, partial theta, plus 1 over r squared sine squared theta, partial squared v, partial v squared. All of that equals to 0. This is Laplace's equation. In spherical coordinates, right? So when would you want to use Laplace's equation in spherical coordinates? Well, my guess probably is if your problem has a spherical symmetry, maybe this is something you ought to look at, right? Now, we've offended Sam, as you know, Sam. He keeps eating hatred of spherical coordinates.
Bye, Sam.
I'm trying to get him to grow as a person, not to hate him too much. One step at a time. So Griffiths, thankfully, throws us a bone here and says, part of the reason I'm using this book and not another book is it gives me license to be lazy. And he says things like, oh, you don't think about this as an undergraduate. This is graduate level stuff. So we're going to assume that partial v is equal to 0. So this would be what's called azimuthal symmetry. What that means for your problem, when would that be the case? See, like rotation about z-axis leaves your boundary condition leaves. See, it's wrong. Doesn't change. Change problem. Something like that. It has a symmetry that if you spin around the z-axis, the problem would be the same. You can't tell one way from another as you go around the z-axis. All right? That's what feels symmetry. So that means, in that context, it's just a two-dimensional problem, right? All we're up against then, in that context, is what? We need to deal with theta and r, right? Theta and r. Now, so not the r in the previous PDF I was looking at, which was math r. This is physics r. It's, square root of x squared plus y squared plus z squared, right? Okay, so basically our product, we're going to do v is a function of r and theta, right? And we'll call that r of r and big theta of theta. Now, if that symbol doesn't give you great joy, you know what? For the sake of making this lecture infinitely more readable, let's call this a t. There you go. All right. Okay. That's not the greatest move because in other places where you do this kind of math, you might have a time dependence. And you might want to save big T for your temporal part of the solution. But here, this is electrostatics, so we've got time. No, we've got no time. So, sorry, I'll stop. But if I plug that up in here, I've got like 0, 1 over r squared, partial r, of what? Like r squared, if I take the r derivative of this, I get r prime t plus 1 over r squared sine theta. Is that a sine squared? If it's squared there, it's squared here too. It's squared, r squared sine squared theta. But partial theta of sine theta r t prime. But we can bring the t out, and what we've got is 1 over r squared partial r of r squared partial r. Bring the t out here. I'll bring the r out here. I don't know. I'll leave it on the other. Fine. Whatever. Bring it out whatever side you want. I'll make my mind eventually. R squared sine squared theta. partial theta. Sine theta partial theta. I'll factor the r out because it's constant here. Right? That's all equal to 0. Now we do the same thing we've done in like the last 5 examples, which is propose a product solution, plug it in, then you divide by the product solution to discover what are the underlying ordinary differential equations you must solve. So here, I'm going to take all this jazz and divide by RT, right? And what that then gives me is 1 over little r squared times big R dr of r squared dr plus 1 over r squared sine squared theta t d theta of sine theta dt d theta equal to a 0. Now you notice something here. Something nice happens here that didn't happen. Maybe cylindrical coordinates are nastier. Maybe actually the reason he doesn't have cylindrical coordinates is exactly the same reason he puts this here. He's avoiding something, isn't he? Like Griffiths, he's a crafty one. By the way, you can't avoid these things in quantum mechanics. The same mathematics comes up in like the solution of the hydrogen atom. To solve the hydrogen atom, you have to solve Schrodinger's equation for spherical coordinates. The same techniques I'm using right now are used there to solve that. Because the same mathematics, separation of variables, is just like, well, harder. But so notice here though, r squared both places, so we just multiply through by the r squared, and then things are ever so much more pleasant, you see, because what we have then is 1 over r ddr of r squared dr plus 1 over sine squared theta times big T dd theta of sine theta dd theta, right? And that is how is it? No. I was wrong. This really is. That really is no sine squared. They're actually, this and that really are different. That was not a typo. That matters because this one survives. So that's not a sine squared, that's not a sine squared, that's not a sine squared, that's not a sine squared. And that matters a fair amount here, actually. Sorry. Okay, so look, again, this has to be constant. And this also has to be constant. Why? Because they're separately functions of just r, functions of just theta, and you can't have a function of both r and theta unless it's constant. All right? So then, following Griffiths, we let GDR of r squared dr equals to L times L plus 1 big R. So in other words, we make this constant here, L times L plus 1. Which makes the other one have to be minus L times L plus 1, by the way, right? So if that gets this piece, then the angular piece has to be similarly, but different. We're up against d theta of sine theta, dt, d theta in my current notation, equals to minus L times L plus 1 times the sine of theta times t. So these are the differential equations, the ordinary differential equations that we must solve in order to solve the spherical Laplace equation. One of these is pretty easy to solve. All right? So like the red one, I'm pretty sure that's just a Cauchy-Euler problem if you look at it, because there's as many, well, it's not quite that, the r squared though, that's funky. I don't know, I'm not sure what this thing is, technically speaking, in the larger world of the differential equations lexicon, I don't know. But I do know that it can be solved, and the solution is actually pretty easy. And I think the form of this solution, in some sense, explains why we labeled the constant as L times L plus 1. So let me just tell you, and we could check this, right? But my claim, let me call these, call this one 1, and I'll call this one 2, all right? So 1 as solution R sub L equals to, the way it works is A R to the L, little r to the L, plus B over little r to the L plus 1. Allegedly that solves 1, right? So if you want, I can drop the L on the R sub L here, but like let's work it out. Like what's dr, drl, dl, udr? You guys help me out with the calculus here. Let's just check on this, so it's not so mysterious. We have A, L, R to the L minus 1, right? Yes. Minus B times L plus 1 divided by R to the L plus 2, right? And then we do R squared times drl dr. What does that give us? That gives us A, L, R to the L plus 1 minus B times L plus 1 divided by R to the L, right? Then our next move is to differentiate that with respect to r and see what happens. Right? So we're differentiating this piece. Let me just do it. So the derivative there is a L times L plus 1, r to the L. And then minus, parentheses, minus L times L plus 1, v over r to the L plus 1. Oh, cool. So that's L times L plus 1 times what? Times AR to the L plus B over R to the L plus 1, which is, of course, L times L plus 1 times R sub L, which is exactly what we want, so it solves. It solves equation 1, right? Right. Great. What about 2? What about 2? 2. How does the solution of 2 go? It's a little bit harder. Let's see here. Am I in the way? Are you guys? Okay, so solution of the other one, namely d theta of sine theta times d theta equal to minus L times L plus 1 sine theta times t, given by t of theta equals to the Legendre polynomial in cosine theta, where PL is the L order Legendre polynomial defined by Rodriguez formula. Rodriguez formula says PL of x, you can calculate as 1 over 2 to the power L times L factorial, the L derivative applied function x squared minus 1 to the L power. Clean. So if you can find someone else to teach all my other classes, then I will have us meet another 3 hours a week and I'll prove that. You know, I don't know. I'm not sure how hard it is to actually prove that. Maybe it's not bad, I don't know, but look, these, let me write out a few of them for you. So P0 of x is just 1. P1 of x is just x. P2 of x is actually 1/2 of 3x squared minus 1. P3 of x is 1/2 of 5x cubed minus 3x. All right. So what does this all mean? When I write PL of theta, what's that actually? What's that about? Like, for instance, if we were talking about T3 of theta, the solution I would be talking about is P3 of cosine theta, and that means 1/2 of 5 cosine cubed theta minus thrice cosine theta. There's like an example of one of the solutions to the angular equation here. Now it turns out that there are other solutions, by the way, to the angular equation, but those will blow up at like angle pi or something. So the potential, and we'll end here today with this, the potential has the following form: V of r theta is equal to the sum L equals 0 to infinity of parentheses a sub L r to the L plus b sub L divided by r to the L plus 1. That's my typical radial solution, right? And then times my typical angular solution, the Legendre polynomial, order L, in cosine theta. That, my friends, is the potential. Now, the difference here is that this is not a Fourier sine series, right? This is something else. So the way we solve for these coefficients in order to make the potential an actual potential, once we actually add more detail, like at the moment, this is just a blank template spherical problem, right? With azimuthal symmetry. To make further progress, we need further boundary conditions. And there's an analog of the Fourier trick here. It's a little bit different, though. It turns out, you'll see that next time, we can actually solve for these and then construct a literal, like an actual solution to the potential. So, for example, one of the problems this allows us to solve is like if you have an otherwise uniform electric field, but you put a conducting sphere in it, then what is the, or disk, I can't remember, like, but this, you can find what's the resulting, like, voltage on such a disk. Things like that. There's a bunch of problems that we could solve with this that we would have trouble solving otherwise. And the other interesting thing is these Legendre polynomials come up in a deeper theoretical discussion called the multipole expansion, which we will hopefully also talk about soon. So anyway, that's where we are at the moment. Thanks, guys.